All right, guys, I wanted to pick up approximately where we left off in class last week. Excuse my voice here. So, we had spoken about the role of lipids in the cell membrane, certainly the phospholipid bilayer, and the importance of regulating polar and nonpolar substances across that cell membrane. Then we looked at briefly the role of carbohydrates in the cell membrane, specifically the glycocalyx, and how that can work to mark a cell as one of our own. So, playing an important function in our immune system. And then lastly, the kind of a meatier part of our three major macronutrients in the cell membrane are the proteins. So, you have passive transport, which does not involve ATP, where we're going from a high concentration to a low concentration. And another way of saying that is to say that we're going down a concentration gradient. In contrast, you have active transport. So with transport proteins, you can have both channel proteins as well as carrier proteins. And then these are also proteins, but they're just being propelled by ATP. So we're going to walk through each one of these. So first of all, channel proteins. I believe we covered this in class, but worth touching upon again. So these channels may be constantly open or gated. And if they're gated, they're either going to be opened by the change in charge across the membrane, or they're going to be opened by the binding of a ligand. And recall that a ligand is simply anything that binds. And when proteins have something bind to it, they like to change shape. Here you're seeing a channel that is constantly open. And again, we're seeing things diffuse from a high concentration to a low concentration. These are lipid insoluble. So, in other words, polar molecules. And again, I know I said this in class as well, but just to illustrate, don't worry about the details of this now, but to attempt to impress upon you the importance of these channels, when we look at the neuromuscular junction, so a neuron communicating with a muscle or a neuron communicating to another neuron, none of that can take place unless you have these voltage gated calcium channels. So action potential comes down, the voltage across this membrane changes, and in comes calcium. Similarly, down here, we have ligand gated channels. So the neurotransmitter is released. And then when it binds, it changes these channels in a way that allows sodium to enter and potassium to leave. Incidentally, this is a type of exocytosis, which is active transport, where the neurotransmitters are essentially spit out of this presynaptic terminal. So much more on that to come in chapter 9. So carrier proteins. So in this case, binding is going to cause that shape change in the protein, and still going passively, still going from a high concentration to a low concentration. So don't lose sight of that. Just because there's a protein involved and just because it's changing shape doesn't mean that the cell is having to expend ATP here. So the three properties of carrier proteins: specificity, competition, saturation. Specificity, right? Just this lock and key concept. This molecule will fit in this protein and this one will not. Competition, we spoke about how molecules, many medicines, work because they are binding to protein sites that are the same shape as other naturally occurring molecules. So here, anandamide, a naturally occurring neurotransmitter, is the same shape as THC. And that's why THC actually has an impact on the human body. So this is where I left off for you guys. So this idea of saturation, I want to impress upon you a little bit more. So with any transport into or out of a cell, there's going to be an optimal rate. And that optimal rate of transport across either this way or this way is really going to be determined by how many transport proteins are available. So on the y-axis here, we're looking at the rate of transport of the molecule. And then here, we're looking at the difference in concentration across the membrane. So are there 30 over here and 2 here? Are there 2 here and 2 there, which would be a perfect balance? So here in this first scenario, you can see that there are two transport proteins available and only one molecule looking to be transported. So the transport rate is going to be low. Oops, sorry guys. Essentially because it's limited by how many molecules are looking to pass. So we're not optimally transporting molecules here. And that may be just fine for the cell, depending on what it is that it's bringing in. Here, right at this tipping point, we are positioned in a way where we have the exact same number of molecules as transport proteins available to move those molecules. And then here, at this point, you can say that we've reached a point of saturation. So the transport rate is going to be limited by the number of transport proteins. So basically all these sites are going to be occupied, and these molecules trying to get past are going to have to wait their turn. And so this is a nice analogy, right? Imagine, 20 people getting off a plane and trying to get taxis to go home. And if there's only 5 taxis available, well, there's going to be a little bit of a line. And those molecules / those people are going to have to wait their turn to be able to get home or to wherever they're going. So that's this idea of saturation of these transporters. Let's skip this for now. So ATP-powered pumps, right? So this is the first time we've looked at active transport. And just bear in mind, too, that a cell is never going to expend energy unless it really has to. So unless it's a function that's particularly important. And that could be the case, require ATP to move solutes across a living plasma membrane because the solute may be either too large for the channels or polar, or something. I think a more intuitive way to think about it is that these are situations where the cell says, you know what, I'm working across or against a gradient. I'm working uphill, if you will, but this is a function so important to my livelihood that I'm going to expend precious money to do so. So there are a number of ATP-powered pumps out there, but I'd like you to know the sodium-potassium pump. So 3 sodium are pushed out for every 2 potassium that are brought in. This is a live link. I highly recommend clicking on this and starting at about this point, about 3 minutes, 20 seconds in. I think he does a great job of highlighting the relevancy here of some of these pumps. And it's also a nice little review. So highly recommend that. At this point here, so these sodium potassium pumps, the reason I chose this from the chapter for you guys to not skip over is that they are essential for functions of both muscle as well as nerve tissue. So without these pumps, you don't get muscle contraction and no nerve impulses. So in other words, no thoughts, no actions, no nothing. So they're that important to the human body. They essentially set up this gradient. They set up this concentration gradient. So here's our sodium potassium pump again. So here come the 3 sodiums, here come the 2 potassiums. And so what you end up with is way more sodium outside the cell and way more potassium inside the cell. You have a little bit of sodium in, you've got a little potassium out. I've heard it described once as a salty banana, and that really stuck with me. So I think a lot of people know bananas are high in potassium. So that would be like the interior of our cell. Here's our potassium. And salt, sodium chloride, yes, but sodium is a big piece of that. So if that helps you to remember where those ions are most concentrated, that could be a useful tool. One other thing that I'd like you to know, so not only is there more sodium out than in, and vice versa with the potassium, but the inside of the cell also rests in a negative state. The inside of the cell is more negative than the outside. So osmosis, so think to yourself for a second, is this passive or active? Hopefully you arrived at passive, right? No ATP is being used. In this case, it's not salts and ions that are going from a high concentration to a low concentration, but it's water that's moving from its high concentration, a hypotonic solution, to its low concentration, or a hypertonic solution. So these YouTube experiments are so elegant, and they make such an impression at the same time. So if you have a situation where salts can pass a membrane, so we're seeing a freely permeable membrane here. So if you have a high salt concentration here, low salt here, and this is, again, a freely permeable membrane, then salts could diffuse and cross over. And that would be a solution to that gradients. And biology biological systems don't like gradients, right? We would like everything to come to an equilibrium whenever possible. Here, this is the situation that we see across a cell membrane, a selectively permeable membrane. So this is the hypertonic side. This is the hypotonic side. Salts can't get through, right? They're not able to cross this selectively permeable membrane, but water can. And water will cross with enough force that you'll actually see the water creeping up these U tubes. So it will counteract gravity to crawl up and reach an equilibrium. This is hopefully review for you all from 111, but considering what would happen to a red blood cell in 3 different situations. So make sure you're comfortable on these terms: hypotonic, hypertonic, and isotonic. Iso meaning the same. Hyper, you could think hyperactive, so high salt. Hypothermia, so low, right? There's some good root words to know, and reviewing these to consider where the movement of water would go in each of these situations. I also posted some good videos by the Amoeba sisters, so if you are a little rusty on osmosis and would like some review, you might also take a look at that clip that I posted. They're short, but I think they're well done. And then lastly, active process via vesicular transport. So movement of bulk matter in this case. So you can either have the cell taking things in, endo, or the cell spitting things out, or exo. So exocytosis, exiting. That would be an example that we saw a little bit ago with the neurotransmitters exocytosing and traveling across the synapse. With endocytosis, if it's a solid particle that the cell is taking in, we refer to that as phago, or the root word here being phage, which means to eat. And you'll see macrophages that we'll get to, big eaters. So that's what you're seeing here. The cell is taking in bacterial particles. And then penocytosis is cell drinking. So I always kind of think about this as the cell kind of sipping on its surroundings, kind of sampling as it travels through its world. And if it helps you to think about a pint in this case for the cell drinking or fluids, that's something else that could work. Take a look at this. You might want to pause it and see if you can answer. And so you have to first ask yourself steroid, so a polar or nonpolar, right? It's going to be nonpolar in nature. And if it's nonpolar, these hormones can they cross the cell membrane, or are they going to have to bind to something on the outside? And hopefully you arrived at being able to bind to something on the inside. So B is the correct answer. They're going to interact inside the target cell's cytoplasm or nucleus. Now, that's not to say that they're not still binding to a receptor. Lock and key mechanisms still apply. So here's a steroid, and here's the steroid coming and binding inside the cell. And again, this would still be a receptor. It would still be specific, but rather than this receptor being on the outside surface of the cell, it's inside. So cortisol, cholesterol, any of our oids, they can come right through. Something like epinephrine is polar, so it's going to have to bind to an integral membrane, integral protein, and come in that way.